Hello everyone, I am Priya from BSc Chemistry Honors Final Year. Today I am going to present a video for visually impaired students. This video is from our organic chemistry. The unit is spectroscopy, nuclear magnetic resonance. Introduction. During the last 6 decades or so, spectroscopic methods such as ultraviolet, infrared, nuclear magnetic resonance, and mass spectroscopy spectrometry have emerged as powerful tools for identification and structure determination of organic molecules. The ultraviolet and infrared spectroscopies have already been discussed in detail. Therefore, in this unit, we will discuss nuclear magnetic resonance spectroscopy, which was discovered by Felix Bloch and Edward Purcell in 1946. The field of NMR spectroscopy has been further divided into number of subfields depending upon the magnetic nucleus being examined. For example, proton magnetic resonance, carbon magnetic resonance, fluorine magnetic resonance, phosphorus magnetic resonance, etc. However, in this unit we will discuss only proton magnetic resonance and the basic principles of NMR spectroscopy. Magnetic properties of nuclei. Like electrons, the nuclei particles, protons and neutrons are also considered to spin about their axis. Further, like electron, each proton and neutron has a spin quantum number of 1 by 2. If the protons and neutrons in a nucleus are not paired, the nucleus as a whole will have a resultant nuclear spin. The numerical value of this nuclear spin quantum number 1 depends upon the number of protons and neutrons having parallel and anti-parallel spins. It is related to the mass number and atomic numbers as follows. In agreement with the above general rules, nuclei such as 1H1 proton, 1H3, 6C13, etc. all have I value 1 by 2. Nuclei such as 2 helium 4, 6C12, 8O16 all have I is equals to 0. It is fortunate for organic chemists that C612 and O 8O16 are non-magnetic, otherwise the NMR spectra of organic molecules would have been much more complex. Nuclei such as 1H2 and 7N14 have I is equals to 1, while 5B10 has I is equals to 3. Now, since an atomic nucleus is associated with charge, therefore like any other rotating charge, it generates a magnetic field along the axis of its spin. Therefore, such a nuclei behaves as a tiny bar magnet and has a characteristic magnetic moment. Nuclear spin states. When a nuclear with I is greater than 0 is placed in an external magnetic field, it is found to have a set of decreased orientations. The applied magnetic field, these various orientations are referred to as spin states. For a nuclei with spin quantum number I is greater than 0, there are 2I plus 1 allowed spin states which different from one another by unity. The various spin states are given by minus I plus 1, I minus 1, and plus I. Thus, it follows that nuclear spin states like electronic and vibrational states are quantized. For example, a proton with I is equals to 1 by 2 has two allowed spin states. 2 1 by 2 plus 1 is equal to 2 designated as minus half and plus half. For chlorine with I is equals to 3 by 2, there are 4 allowed spin states which are minus 3 by 2, minus half and plus 3 by 2. In the absence of a strong external magnetic field, the nuclear spins of magnetic nuclei are orientated randomly. However, these magnetic nuclei are placed between the poles of a strong magnet. They either align with the field or opposite to the field. When a compound containing hydrogens is placed in an applied external magnetic field, the protons may assume one of the two possible orientations. The external magnetic field, these two possible orientations do not have the same energy and hence are not equally populated. The orientation in which the spins of the nuclear magnets are aligned parallel to the external magnetic field is slightly lower in energy, and hence this spin state is slightly favored over the other orientation in which the spins of the nuclear magnets are aligned anti-parallel to the external magnetic field. The difference in energy between the two spin states is designated as del E. In general, the value of del E is very small, but the magnitude depends upon the strength of the applied magnetic field as shown in figure 2.3. From figure 2.3, it is clear that when H naught is equal to 0, del E is equal to 0. In the absence of a magnetic field, the two spin states of a proton have equal energy. However, as the strength of the applied field increases, the energy difference between the two states increases. As a field strength of 14100 G or 1.41 T, del E is equal to 2.39 into 10 to the power minus 5 kilojoule mole inverse, while when H naught is equal to 23500 G or 2.35 T, del E is equal to 3.97 into 10 to the power minus 5 kilojoule mole inverse. Tesla are units of magnetic field in CGS and SI units respectively. Principle of nuclear magnetic resonance. To understand the principle of nuclear magnetic resonance, let us consider the motion of a common spinning top. When the spinning top is disturbed a little, its spinning axis will trace out a circle perpendicular to the Earth's gravitational field, as shown in figure 2.4. Such a motion is called precession. In a similar way, when a nuclear magnet is placed in an external magnetic field, it will experience a torque which will tend to align it with the field. Since the nuclear magnet is spinning, it will not align with the external magnetic field but will precess around it with a certain angular frequency called the precessional frequency or the Larmor frequency. The frequency at which a proton will process will depend upon the strength of the applied magnetic field. Stronger the applied field, higher is the professional precessional frequency for a proton. If the applied magnetic field is 14100 Gauss, the precessional frequency will be 60 megahertz. Since a proton has two allowed spin states, plus half and minus half, it can precess in two principal orientations, one aligned with the applied field and the other opposed to the applied field. It is possible to induce transitions between these two orientations by irradiating the precessing nuclei with radio waves of a correct frequency. When the precessional frequency of the nuclei is exactly equal to the frequency of the electromagnetic radiations, the absorption occurs and the nuclei in lower energy spin state flip to the higher energy spin state. When this occurs, the nucleus and the radio frequency beam are said to be in resonance, and since the resonance is due to magnetic properties of the nuclei, it is called nuclear magnetic resonance, abbreviated as NMR. The exact amount of the radio frequency energy needed for resonance depends upon the strength of the external magnetic field on the nucleus being irradiated. Del E is equal to H mu is equal to lambda H by 2 pi dot H naught, where del E energy difference between the two spin states, H is Planck's constant, gamma is gyromagnetic ratio. It is a ratio of magnetic moment to angular momentum and is constant for each nuclei. For a proton, the value of gamma is 26750. It may, however, be noted here that a NMR instrument with a magnetic field strength of 1.41 T and operating at a constant RF of 60 MHz can induce transitions only among proton spin states in a molecule and is not useful for other nuclei. Therefore, separate instruments are required to observe transitions in the nuclei of other elements such as carbon, phosphorus, fluorine, etc. However, the modern, more expensive Fourier transform instruments which are commonly used these days can be used to observe the resonance of nuclei of several different elements in a single instrument. Instruments with 200 and 300 MHz are now quite common, and instruments with frequencies up to 800 MHz are found in the advanced research institutions and bigger universities. We have discussed above that the energy difference between the two spin states of a proton at 60 MHz is just 2.39 into 10 to the power minus 5 kilojoule mole inverse. Since the energy difference is too small, thermal energy due to room temperature is sufficient to populate both the spin states. There is, however, a slight excess of nuclei is the lower energy spin state. The magnitude of this difference can be calculated by using Boltzmann distribution equations. The following equation gives the Boltzmann ratio of nuclear spins in the upper and lower states. N upper upon N lower is equal to e की power minus del E upon kt is equal to e to the power minus h mu upon kt, where del E is the energy difference between the upper and the lower spin states and k is the molar gas constant. Using this equation, we can calculate that at 298 Kelvin for an instrument operating at 60 MHz, there are 1 0.00009 nuclei in the lower spin state for 1.0000000 that occupy the upper spin state. In other words, in approx 2 million nuclei, there are only 9 more nuclei in the lower spin state. These excess nuclei are the ones which are responsible for the NMR signal. When the 60 MHz radiation is applied, it is not only induced transitions upward but also simulates transitions downward. When the populations of the two states become exactly equal, we observe no net signal. This situation is called saturation. Therefore, while performing an NMR experiment, care must be taken to avoid saturation. Saturation is achieved quickly if the power of the RF signal is very high. If we increase the operating frequencies of the NMR instrument, the energy difference between the two spin states increases, which causes an increase in excess population at 300 MHz and 96 at 600 MHz. In other words, at higher operating frequencies, more nuclei can undergo transitions. Therefore, the sensitivity of the instrument increases and the resonance signals are stronger. PMR spectrum origin or signal. In principle, a PMR spectrum can be obtained by placing the substance containing hydrogen nuclei or protons in a magnetic field of constant strength and passing electromagnetic radiations of varying frequencies through the substances and observe the frequencies at which radiation is absorbed. In practice, however, it has been found more convenient to keep the frequency of the electromagnetic radiation constant and vary the strength of the magnetic field. At some value of the field strength, the energy required to spin the proton matches the energy of the electromagnetic radiations. At this stage, absorption occurs and a signal is observed. Such a spectrum is called a PMR spectrum. The PMR spectrum is a plot of intensity of absorption along y-axis against magnetic field strength along x-axis. By convention, magnetic field strength increases from left to right across the chart. Since the magnetic field strength and the frequency are related by the equation mu is equal to mu h naught upon hi is equal to lambda h naught upon 2 pi. The position of any absorption signal along the x-axis can be expressed in either field or the frequency units. A typical NMR absorption signal is shown in figure 2.5. We have discussed above that a PMR signal is obtained at some value of the field strength at which the energy required to flip the proton become equal to the energy of the electromagnetic radiation. Therefore, we may expect that all the protons in an organic molecule will absorb at exactly the same field strength. Consequently, the PMR spectrum would consist of a single signal, and it will be of little use to the organic chemist. In practice, it has been found that all the protons do not absorb at the same frequency. This is due to the reason that the frequency at which a proton absorbs depends upon the magnetic field which that proton actually feels, and the effective field strength is not exactly the same as the applied magnetic field. This effective field strength which a proton feels depends upon its local environment, electron density around that proton, and the presence of other protons in its neighborhood. In other words, each proton, or more precisely each set of equivalent protons, will have a slightly different environment than every other set of equivalent protons, and hence will absorb at slightly different applied field strengths to experience the same effective field strength at which the absorption occurs. Thus, it follows that of a given radio frequency, same effective field strength at which the absorption occurs. Thus, it follows that a given radio frequency, the protons having different environments experience the same effective field strength but absorb at different applied field strengths. Since in a PMR spectrum, absorption is plotted against the applied field strength. A PMR spectrum will consist of a number of absorption signals which would be very useful in determining the structure of molecules. NMR spectrometer. We have discussed above that there are two ways to scan an NMR spectrum, either one by keeping the magnetic field H naught constant and changing the frequency of the radio frequency oscillator, or by second keeping the frequency of the radio frequency oscillator constant and changing the magnetic field. In practice, however, NMR instruments which work at constant radio frequency are used since they are easier and cheaper to construct. Such instruments are called continuous wave or CW spectrometer. The scheme diagram of an CW NMR spectrometer is shown in figure 2.6. It consists of the following parts: a powerful electromagnetic whose strength can be varied, a radio frequency generator, a detector which monitors the absorption of energy and amplifies the electronic signal, a recorder which records the spectrum on a chart paper which is calibrated in frequency and ppm units, a 5 millimeter wide long sample tube. This is the diagram. A sample is dissolved in a suitable solvent which does not contain protons and is spun around its axis to ensure that all parts of the solution experience a relatively uniform magnetic field. In between the poles of the magnet, there is a coil which is attached to a 60 MHz RF generator. This coil supplies the electromagnetic energy used to change the spin orientation of the protons. Perpendicular to the RF oscillator coil is a detector coil. More advanced NMR spectrometers, known as Fourier transform NMR spectrometers, are now available. In these instruments, magnetic field is held constant and the radio frequency is varied. While a CW spectrometer takes 2 to 5 minutes to scan the PMR spectrum, FT NMR instruments can record a spectrum within 5 seconds. Solvents used in PMR spectroscopy. Any solvent which does not contain protons can be used in PMR spectroscopy. The most widely used solvent is deuterated chloroform CdCl3. Other solvents which are commonly used in PMR spectroscopy are carbon tetrachloride, deuterated acetone, deuterated dimethyl sulfoxide, deuterated benzene. Trifluoroacetic acid is also used sometimes even though it contains a protons. The reason being that this acidic proton absorbs at a very low field and hence does not interference with the absorptions of most of the compounds which usually occur in the range to 0 to 10 del. Number of NMR signals, equivalent and non-equivalent protons. We have discussed about that in a given molecule, protons with different environments absorb different field strengths, while protons which have the same environmental absorb at the same applied field strength. A set of protons are said to be equivalent if they have the same environment and non-equivalent if they have different environments. Since each set of equivalent protons produces a different signal, therefore the number of signals in an PMR spectrum tells us as to how many different sets of equivalent protons and how many different types of protons are present in a molecule. In the most of the cases, it is possible to predict the different types of protons present in a given molecule simply by looking at the structure. But this is not always easy. Therefore, we must devise a method by which we can accurately tell as to how many different kinds of protons are present in a molecule. In this method, we imagine that each of the hydrogen atoms or protons is substituted by some other atom Z. If the substitution of either of the two protons by Z gives either the same or in enantiomeric products, the two protons are chemically equivalent, otherwise not. It may be noted that in general, chemically equivalent protons are also magnetically equivalent and thus give rise to the same signal in the PMR spectrum. Let us now illustrate this method by considering a few examples. The molecule of ethyl chloride contains 3 methyl and 2 methylene protons. A replacement of a methyl proton would give ZCH2CH2Cl and replacement of a methylene proton will give CH3CHZCl. These are obviously different products, therefore methyl protons are not equivalent to methylene protons. However, it may be noted that the 3 methyl protons are equivalent amongst themselves since the replacement of any one of them gives the same product. On the other hand, replacement of either of the two methylene products would give one of the two enantiomeric products. Such pairs of protons are called enantiotopic protons. The environments of these two protons are mirror images of each other and hence are magnetically equivalent to each other and thus gives rise to one signal if the PMR spectrum is scanned in an acryl solvent. However, in a chiral solvent, the two protons would become magnetically non-equivalent and would give two signals. From the above discussion, it follows that ethyl chloride contains only two types of protons and thus gives two PMR signals. Proceeding on similar lines, we can easily predict the number of different types of protons present in the following molecules. Let us now consider a molecule of 2-bromopropene. It has 3 methyl and 2 vinylic protons. The 3 methyl protons are obviously equivalent among themselves since replacement of each one of them gives the same product. On the other hand, replacement of either of the vinylic protons produces one of a pair of distereomeric products. Such pairs of protons are called distereotopic protons. The environments of these two protons are neither identical nor mirror images of each other and hence are non-equivalent. As such, each of these would give a separate PMR signal. Thus, 2-bromopropane contains three kinds of protons A, B and C in the formula given below and hence gives the three NMR signals. Similarly, in 1,2-dichloropropene, the two protons on C1 are diastereotopic and thus gives rise to separate signals. Thus, the molecule of 1,2-dichloropropane gives 4 PMR signals. Proceeding on similar lines, we can easily predict the number of different types of protons present in following molecules. Position of signals, shielding and de-shielding. We have discussed above that the number of signals in a PMR spectrum tells us how many different types of protons are present in a given molecule. In a similar way, the position of signals tells us what kind of protons they are. In other words, the position of signals tells us the actual environments of the various protons and thus indicates the nature of protons, whether the protons are aliphatic, aromatic, vinylic, acetylic, or are adjacent to heteroatoms such as oxygen, nitrogen, sulfur, halogens, etc. When a molecule is placed in a magnetic field to get its PMR spectrum, the applied magnetic field causes the circulation of electrons surrounding the protons. This circulation of electrons produces a secondary magnetic field called the induced magnetic field. This induced magnetic field may either oppose or reinforce the applied magnetic field. For example, circulation of electrons in pi bond pi bond surroundings the protons generates an induced field which opposes the applied magnetic field. On the other hand, circulation of electrons, particularly the pi electrons, generates an induced field which may either oppose or reinforce the applied field acting upon a proton depending upon its location in the induced field. For example, circulation of pi electrons in benzene derivatives produces an induced field which reinforces the applied field at proton. Similarly, the circulation of pi electrons of the CH is equal to 0 group reinforces the applied field at the proton. In contrast, the circulation of pi electrons of acetylene produces an induced field which opposes the applied field at the proton. When the induced field opposes the applied field, the actual field acting on the proton decreases and the proton is said to be shielded. In order to get an absorption signal from the shielded proton, the applied field has to be increased somewhat to reach the same effective field strength at which the absorption occurs. The shielding shifts the absorption upfield. On the other hand, when the induced field reinforces the applied field, the actual field acting on the process increases and the proton is said to be de-shielded. Obviously, to get an absorption signal from a de-shielded proton, the applied magnetic field is to be decreased somewhat so as to achieve the same effective field strength at which absorption occurs. Thus, de-shielding shifts the absorption downfield. For example, the induced field opposes the applied field at the protons of acetylene while it reinforces the applied field at the protons of benzene. As a result, acetylenic protons are shielded and absorbed upfield whereas benzene protons are de-shielded and absorbed downfield. Chemical shift. The shift in the position of PMR signals resulting through shielding and de-shielding by circulation of electrons in chemical bonds is called chemical shift. Protons in most of the usual types of organic compounds absorbs over a range of 700 Hz at a field strength of 14100 Gauss. At this field strength, protons absorb a frequency of about 60 into 10 to the power 6 Hz. The shielding and de-shielding of protons by electrons produce very small changes in the strength of the applied magnetic field. These small changes in the magnetic field strength cannot be determined accurately. Consequently, the absolute position of the PMR signal cannot be obtained from the instrument as is the case with UV and IR spectrometers. However, relative proton frequencies can be radially determined with an accuracy of about plus 1 minus 1 Hz. Therefore, chemical shifts of protons are expressed in Hz or CPS with reference to a particular standard. It may be noted here that even though the chemical shifts are expressed in Hz, it does not mean that the frequency of the electromagnetic radiation is being varied. In actual practice, it is the magnetic field which is varied since the frequency and the strength of the magnetic field are related by the equation V is equal to gamma h naught upon 2 pi. The frequency units are justified. The most commonly used reference for PMR spectroscopy is tetramethyl xylene. It is chosen as a reference compound for the following several reasons. It has 12 magnetically equivalent protons, therefore a very small amount of the TMS produces a relatively large single sharp signal. TMS protons absorbs at a field much higher than the protons in the most of the usual organic compounds. This is due to the reason that silicon is more electropositive than carbon. It thus pushes electrons into the methyl groups of TMS by its plus I effect. As a result, the protons of CH bonds in TMS have high electron density around them and hence are highly shielded. It is chemically inert and is also highly volatile. Therefore, after the spectrum has been scanned, the precious sample can be recovered by the removal of TMS by evaporation. It is highly miscible with most of the organic solvents. Units of chemical shift. We have stated above that the chemical shifts are expressed in Hertz as the difference in the frequencies of absorption of a particular proton in the organic compound and the proton of the reference compound. But we know that the chemical shift is proportional to the strength of the applied field or to the radio frequency used in the instrument. Since different NMR spectrometers have different oscillator radio frequencies such as 40, 60, 100, 200 MHz, it is desirable to express the chemical shift in some unit which is independent of the field strength. The most commonly employed unit is parts per million of the oscillator frequency. To do this, the chemical shift in Hertz is multiplied by a factor of 10 to the power 6 and then divided by the oscillator frequency of the instrument. For example, the protons of acetone absorbs at 126 Hz downfield from TMS at 60 MHz. Its chemical shift is 2.1 ppm. However, if the spectrum of acetone is scanned at 100 MHz, the protons will absorb at 210 Hz downfield from TMS, but its chemical shift will still be 2.1 ppm. It may be noted here that the factor 10 to the power 6 is included in the numerator simply for convenience to avoid the fractional values. From the above discussion, it follows that the chemical shifts when reported in ppm are dimensionless and are independent of the field strength or the oscillator frequency of the instrument. Therefore, they are simply a function of the chemical environments of the protons in the given organic molecule. Scales of the chemical shift. In terms of ppm, the chemical shifts are expressed in the following two scales. The delta scale, where delta is equal to del mu in hertz into 10 to the power 6 upon oscillator frequency. The tau scale, where tau is 10 minus delta. On the delta scale, the position of TMS signal is taken as 0.0 ppm and most of the chemical shifts have delta values between 0 to 10. A small delta value indicates a small downfield shift while a large delta value has a large downfield shift. In other words, shielded protons have low delta values whereas de-shielded protons have large delta values. On the tau scale, the position of the TMS signal is assigned a value of 10 ppm and most chemical shifts have values between 0 to 10. Here a small tau value refers to an absorption at low field and a high tau value indicates a high field absorption. In other words, shielded protons have high tau values whereas de-shielded protons have low tau values. It may be noted here that some compounds have protons which are even more shielded than those of TMS. Their chemical shifts are assigned either negative delta values or more than 10 tau values. Chemical shifts of different types of protons. We know that the chemical shifts of a proton depends upon its electronic environment. In a given molecule, protons With same environments, equivalent protons have same chemical shifts, while protons in different environments, non-equivalent protons have different chemical shifts. In other words, a proton with a particular environment will have almost the same chemical shift regardless of the molecule in which it occurs. Therefore, from the position of the signals in PMR spectrum of a sample, we can safely tell as to what is the electronic environment of each type of protons in that sample. The chemical shifts of different kinds of protons relative to TMS are given in table 2.1. It should be noted that the chemical shifts given for each types of protons may show a slight variation, since the chemical shift of a proton also depends to some extent on the overall structure of the molecule, solvent, temperature and concentration of the sample used for scanning the PMR spectra. From the table 2.1, it is evident that chemical shifts of protons in majority of the organic molecules vary from 0 to 12 ppm, and this range can be easily divided into the following 7 regions as shown in table 2.2. Factors affecting chemical shifts. Some of the important factors which influence the proton chemical shifts are inductive effects, anisotropic effects, hydrogen bonding. Inductive effect. The proton chemical shifts increase as the electronegativity of the atom attached to the carbon atom bearing hydrogens increases. This is due to the reason that -I effect of the electronegative atom decreases the electron density around the proton, which causes de-shielding. Thus, higher the electronegativity, higher the de-shielding, and hence higher the delta value of the chemical shift. This is illustrated in following table 2.3. Anisotropic effects. We have discussed in section 2.8 that the circulation of pi electrons may either shield or de-shield a proton depending upon its location around the pi electrons. Such effects, which depends upon the orientation of the proton relative to the induced field, are called anisotropic effects. Thus, mainly due to the anisotropic effect, the partially due to sp2 hybridization, the olefinic and aromatic protons are much more de-shielded than protons on a sp3 hybridized atom. Aldehydic protons appear even further downfield than aromatic protons, mainly due to the anisotropic effect and partially due to -I effect of the electronegative oxygen atom, which further reduced the electron density around the proton. Hydrogen bonding. Protons which exhibit hydrogen bonding show variable absorption positions over a wide range. Since H bonding decreases the electron density in the OH bond, therefore the proton involved in H bonding gets de-shielded. Further, stronger the hydrogen bond, more shielded is the proton. The extent of hydrogen bonding, however, depends upon concentration, temperature and nature of the solvent. Thus, in concentrated solutions, H bonding predominates, and H bonded protons appear in the range 4 to 5 delta, but at high dilution H bonding does not occur and the OH bond protons absorbs in the range 0.5 to 1 delta. Important generalizations. On the basis of the above discussion, the following important generalizations can be made regarding molecular structure and chemical shifts. Electronegative atoms such as oxygen, nitrogen and halogens de-shield the proton and the absorption shifts downfield. Conversely, electropositive atoms such as silicon increase the electron density around the proton. As a result, proton gets shielded and the absorption shifts upfield. The sigma electrons of the carbon-carbon bonds de-shield and the protons attached to it. Thus, a 3-degree hydrogen is more de-shielded than a 2-degree hydrogen, which in turn is more de-shielded than a 1-degree hydrogen. However, hydrogen attached to carbon in the highly strained cyclopropane ring absorbs at the highest field around 0.5 delta. Thus, chemical shift in delta values decreases in the order 3 degree, 2 degree to 1 degree to strained ring. Due to anisotropic effect, the pi electrons of aromatic, olefinic and carbon oxygen double bonds have strong de-shielding effect on the attached protons. The order of de-shielding is 9 to 10 delta, is greater than 7.3 delta, is greater than 4.5 to 5.9 delta. Due to strong electron withdrawing effects, the carbonyl group carbon oxygen de-shield the protons on the alpha carbon. Similarly, benzylic and allylic protons are de-shielded relative to protons on saturated carbon atoms. Hydrogen bonding de-shielded the protons in carboxylic acids due to the resonance and the strong minus I effect of the oxygen atom. The electron density around hydrogen decreases significantly and thus the proton of the oxygen hydrogen group of acids gets highly de-shielded and thus absorbs in the region 10.5 to 12 delta. Peak area and proton peak area and proton counting. We have discussed above that the number of signals in the PMR spectrum of an organic compound tells us as to how many different kinds of equivalent protons are present, and their positions of chemical shifts tells us too as to what type of protons each signal represents. Besides these, it is also possible to determine the number of protons giving rise to a particular signal by measuring the relative intensities of the signals. The intensity of a PMR signal means the area under that absorption peak and not nearly the height of the peak. Further, the area under a particular peak is directly proportional to the number of equivalent protons giving rise to that signal. In other words, the relative areas under the different peaks gives the relative number of protons of different kinds present in a molecule of a given compound. The peak area of different signals in a PMR spectrum are measured by an electronic integrator, and the process is called integration. The integration of signals are shown on the chart in the form of a stepped by curve called integral curve. The height of the steps are then proportional to the peaks areas. Since the NMR chart paper is generally cross heads, we can easily calculate the height of steps by simply counting the number of squares. The relative peak areas are then converted into a simple whole number ratio by dividing each area by the lowest area. This ratio or some simple multiple of its gives the exact number of protons of each kind present in the molecule. Consider for example the spectrum of toluene as given in figure 2.11. The spectrum contains two peaks, one at delta 2.32 due to the methyl protons and other at delta 7.13 due to aromatic protons. Their ratio of squares is 6 ratio 10 or 3 ratio 5. Thus the actual number of methyl and ring protons is 6 and 5 respectively. Splitting of signals, spin coupling. We have discussed above that all the number of signals in a PMR spectrum is equal to the number of different types of protons present in the molecule. In other words, every set of equivalent protons gives one PMR signal. This is of course true for some molecules, but the PMR spectra of the most of the organic compounds are much more complicated than we can expect in view of the above statement. To illustrate this, let us consider the PMR spectrum of 1,1,2 tribromoethane. This compound contains two kinds of protons and hence its PMR spectrum is expected to show only two peaks. But its actual PMR spectrum shows as many as 5 peaks. Similarly, the PMR spectrum of 1,1-dibromoethane shows 6 instead of 2, and that of ethyl bromide contains 7 instead of 2 peaks. Thus, it follows that the signal from each set of equivalent protons does not appear as a single peak but usually appears as a group of peaks. This is commonly known as splitting of PMR signals. The splitting of PMR signals has been found to depend upon the environment of the absorbing proton, the protons on the adjacent atoms. In other words, the splitting of the PMR signal can be explained by assuming that the magnetic field experienced by one set of equivalent protons is influenced by the spin arrangement of the protons present on the adjacent atoms. To illustrate that, let us consider two adjacent carbon atoms, one carrying two secondary protons and the other carrying one tertiary proton. The actual magnetic field, which is a secondary proton, feels at any particular moment is increased or decreased slightly by the spin orientation of the nearby tertiary protons. The field would be increased if the spin of the tertiary proton is found to be aligned with the field at the moment, and decreased if the spin of the tertiary proton is found to be aligned against the applied field. But it is reasonable to assume that at a given moment the probability of assigned alignment of the spin of the tertiary proton with or against the applied field must be equal. In other words, half of the molecules of the secondary proton will feel an increase, absorb slightly upfield. Thus, the absorption signal is split up into two peaks called the doublet with equal intensities. Since this splitting of a PMR signal is due to different spin states of the adjacent protons, it is referred to as spin-spin splitting or spin-spin coupling, and the number of peaks to which a given signal is split is called the multiplicity of the signal. Thus, the multiplicity of the signal protons in the above example is a doublet. Let us now examine the multiplicity of the tertiary proton signal. Evidently, it would be affected by the spin combinations of the two adjacent secondary protons. Now there are four equally probable combinations of spin alignment for these two protons, out of which two combinations are equivalent as shown in figure 2.14. Thus there are only three effective combinations. Consequently, the tertiary proton fills any one of the three fields, and hence the signal is split into three equally spaced peaks called a triplet. The relative intensities of three peaks in this triplet are 1:2:1. The central peak will be almost double in intensity than the two outer peaks due to the combined probability of the two equivalent combinations. It is interesting to note that the spacing between the two peaks of the doublet is exactly the same as the spacing between any two adjacent peaks of the triplet. This is due to the reason that spin-spin coupling is a reciprocal process and the coupled protons affect each other to same extent. This spacing in hertz is called the coupling constant. In the light of the above arguments, the PMR spectrum of 1,1,2-tribromoethane consists of one doublet due to the proton on C2 and one triplet due to the proton on C1. Further integration has revealed that the total area under the doublet is twice the area under the triplet, indicating that the doublet is due to two protons and the triplet is due to one proton. Let us now consider a system of two adjacent carbon atoms, one carrying three primary protons and the other one tertiary proton. We have discussed above that a PMR signal is split into a doublet by one nearby proton and into a triplet by two equivalent nearby protons. Working on similar lines, we can safely predict that three equivalent nearby protons will split a signal into four peaks, called the quartet, with 1:3:3:1 intensities. It can be easily seen from figure 2.15 that there are 8 possible combinations of the spin states of 3 primary protons. However, there are 2 sets of 3 equivalent combinations. Therefore, there are only 4 effectively combinations. Consequently, the tertiary proton fills any one of these 4 fields at any moment. Therefore, the tertiary proton signal is split up into 4 equally spaced peaks called the quartet. Similarly, we can predict that the signal due to 3 primary protons will be split into 1:1 doublet and the one nearby tertiary proton. In the light of the above arguments, the PMR spectrum of ethyl bromide consists of a 1:1 doublet due to C2 protons and a 1:3:3:1 quartet due to C1 protons. Further integration has revealed that the total area under the doublet is 3 times the area under the quartet, indicating thereby that the doublet is due to the 3 equivalent protons and the quartet is due to 1 proton. Lastly, let us consider the molecule of ethyl bromide. Its PMR spectrum, as expected, show as a 1:3:3:1 quartet due to 2 equivalent methylene protons and a 1:2:1 triplet due to 3 equivalent methyl protons. Since the two protons on the carbon atom carrying the bromine atom are de-shielded due to -I effect of the bromine atom, the two proton quartet will appear at a lower field than the three proton triplet. In actual practice, it has been found to be so. The three proton triplet absorbs at delta 1.7 while the two proton quartet absorbs at delta 3.4. Here again it will be found that the area under the triplet is 1.5 times the area under the quartet, indicating thereby that the triplet is due to the three equivalent protons and the quartet is due to two equivalent protons. Rules for spin-spin splitting of proton signals. In general, the following rules are quite helpful in predicting the spin-spin splitting of proton signals. Splitting of a proton signal is only caused by non-equivalent neighboring or vicinal protons. Protons on the adjacent carbon atoms. By non-equivalent protons, we mean protons which have different chemical shifts. For example, the PMR spectrum of ethylene dichloride does not show splitting of proton signals since the vicinal protons are equivalent to one another. Splitting of one proton by another proton on the same carbon. Geminal coupling is seen only when the two geminal protons are non-equivalent. For example, we do not observe splitting between the two vinyl protons of isobutylene since these are equivalent. On the other hand, we do observe the splitting between the two vinyl protons of two bromopropane since they are non-equivalent. Further, the mutual splitting of the protons separated by more than two atoms is normally not observed. For example, in the compound 1,2-dibromo-2-methylpropane, we do not observe splitting between 6 methyl protons on one hand and 2 CH2 protons on the other hand. For similar reasons, we do not see coupling between the ring and the side chain protons in alkyl benzenes. The number of peaks into which a given proton signal is split is equal to 1 more than the number of vicinal protons. In other words, the multiplicity of a proton signal is given by n plus 1, where n is the number of vicinal protons. This is also called the n plus 1 rule. Thus, a PMR signal is split into a doublet by 1 vicinal proton, into a triplet by 2 vicinal protons, into a quartet by 3 vicinal protons, into a quintet by 4 vicinal protons, and so on. In general, these relative intensities of the various peaks of a multiplet correspond to the coefficients in the binomial expansion, where n is the number of vicinal protons. These relative intensities of the components of a multiplet can be easily remembered by the Pascal triangle. 1 singlet, 1:1 doublet, 1:2:1 triplet, 1:3:3:1 quartet, and so on. All the peaks of a given multiplet, doublet, triplet, quartet, do not have exactly the same intensity as predicted above. In general, it has been found that the inner peaks, means peaks nearer the other coupled multiples, are larger than the outer peaks. For example, the doublet and the triplet in the PMR spectrum of 1,1,2-tribromoethane are expected to be symmetrical, but are actually not symmetrical. Similarly, the quartet and doublet in the spectrum of ethylene bromide should be as shown in figure 2.17, but are observed as shown in figure 2.17d. Likewise, the quartet and triplet in ethyl bromide should be shown in figure 2.17e, but are actually observed as shown in figure 2.717f. Perfectly symmetrical intensities are observed only when the separation between multiplates is very large than separation within multiplates, when the chemical shifts difference is much larger than the coupling constant. The distance between the adjacent peaks in a multiplet is called the coupling constant. It is a quantitative measure of the effectiveness of spin-spin coupling. It is denoted by the symbol J, and the coupling constant between two protons marked HA and HB is represented as ZA. The value of the coupling constant is expressed in Hertz or cycles per second. Unlike the numerical value of the chemical shifts expressed in Hertz, the numerical value of J expressed in Hertz is independent of the applied field strength, but depends upon the molecular structure. Therefore, coupling constant measured on a 60 MHz NMR instrument will be the same as those measured on a 300 MHz NMR instrument. If a compound has two mutually coupled protons, then the coupling constant due to splitting of one proton by the other is the same as the coupling constant due to the splitting of second proton by the first. In other words, mutually coupled protons have the same numerical value of the coupling constant. For example, consider a theoretical system having the grouping CHP, CHA and CHA. Here the signal due to the two equivalent protons HA is split into a 1:1 doublet by proton HB. with a coupling constant of JAB. Likewise, the signal due to HB is split by two equivalent protons HA into a 1:2:1 triplet having the same coupling constant ZAB as shown in figure 2.18. Magnitude of coupling constant. The numerical value of the coupling constant depend on the number and kinds of intervening bonds, spatial positions of the two coupled protons, and the structure of the molecule as discussed below. For vicinal protons, protons attached to adjacent carbon varies from 2 to 14 Hz depending upon the spatial position of the coupled protons and the molecular structure. In case of compounds in which free rotation is possible, protons with anti-conformation have J is equal to 5 to 14 Hz, while protons with Gaussian conformation have J is equal to 2 to 6 Hz. In compounds of the type CH3CH2X, the typical value of coupling constant lies between 6.5 to 7.5 Hz. For alkenes, trans protons have higher J values than cis protons. For geminal protons, non-equivalent protons attached to the same carbon, the value of J varies from 10 to 18 Hz depending upon the dihedral angle and the molecular structure. However, for vinylic protons, J varies from 1 to 4 Hz. For allylic protons, J is equal to 2 to 13 Hz. For aromatic protons, J decreases as the distance between the two protons increases. For example, the value of the coupling constant is sometimes very useful in determining the structure, particularly the configuration of the molecules. Magnetic equivalence of the protons. It has already been discussed that the magnetic equivalence or non-equivalence of protons is very important in PMR spectroscopy since it determines both the number of signals and their splitting. Now it has been found that magnetic equivalence of protons in some cases depends upon the rate at which certain molecular changes such as rotation around single bond occur. Therefore, PMR spectroscopy can also be used to study these molecular changes. To illustrate this, let us compare a PMR spectroscopy with a slow speed automatic camera. Suppose we want to get the photograph of the spokes of a rotating wheel with his camera. Clearly, the nature of the photograph will depend upon the speed with which the wheel rotates. If the wheel rotates at a very low speed, the photograph will show all the individual spokes quite sharply. If the wheel rotates little faster, then the photograph will show only blurred spokes. If, however, the wheel is rotating very fast, the photographer will show just a circular smear. In a similar way, if the molecular changes occur slowly, the PMR spectrometer will see the portion proton in each of its environments. If, on the other hand, the molecular changes occur at a relatively faster rate, the spectrometer will not be able to distinguish between the changing environments but will see the proton in its average environment. Let us now consider the molecule of ethyl bromide. It can exist in three equally stable standard conformations 1, 2 and 3 which are identical in all respects except that in each case a different proton occupies the antiposition, the bromine atom. In each of these conformations, one of the protons which is anti with respect to the bromine atom is different from the other two which are gauche. Since the three conformations are equally populated, we should see two PMR signals with a relative intensity of 2:1, but still the three methyl protons give only one PMR signal. This suggests that all the three methyl protons are magnetically equivalent. This is due to the reason that the rate of interconversation of 1, 2 and 3 by rotation through carbon-carbon single bond is very fast. As a result, the PMR spectrometer sees all the three methyl protons in the same average environment and hence only one PMR signal is obtained. A similar situation occurs in case of cyclohexane molecule. It contains 12 protons, 6 of which are axial and the remaining 6 are equatorial. Since the rate of interconversion of one chair conformation into other by rotation about carbon-carbon bond is very fast, the PMR spectrometer sees only an average environment in which each proton is half axial and half equatorial. As a result, at room temperature, cyclohexane shows only one sharp signal for all the 12 protons. If, however, by lowering the temperature, we could sufficiently slow down the rate of rotation about single bonds, the PMR spectrometer might be able to distinguish between the individual environments of each set of 6 equivalent protons, and thus then we should be able to see two signals. This is exactly what happens. Thus, when cyclohexane is gradually cooled down, the single sharp peak observed at room temperature is seen to broaden and then tends to split around 200 K. And finally, at 173 Kelvin, it is split into two sharp peaks, one due to axial protons at around delta 1.2 and other due to equatorial protons at around delta 1.7. This process of broadening of single signal at decreasing temperatures and their ultimate splitting into separate peaks has been used to estimate the E activation for rotation about carbon-carbon single bonds. Indeed, by using the method, the energy barrier of 46 kJ mole inverse was calculated for rotation about carbon-carbon bonds in cyclohexane. Applications of PMR spectroscopy. PMR spectroscopy has been extremely useful in the study of organic chemistry. Some of its important applications are discussed below. Identification of substances like IR spectrum. PMR spectrum can also be used as a fingerprint of the substance. If the PMR spectrum of a given sample is exactly the same as that of a known compound, the given compound must be identical with the known compound. In this way, PMR spectroscopy can be used to stabilize the identity of substances. Determination of molecular structure. PMR spectra are often very complex, but this complexity is not a disadvantage but is often useful in determining the molecular structure since it makes the spectra characteristics. Furthermore, even the complex spectra can be made interpretable by using the techniques of deuterium labeling and double resonance. Thus, PMR spectroscopy is increasingly being used as a versatile tool for structure determination of organic compounds, identification of reaction products. Wherever in a reaction two or more products are theoretically possible, PMR spectroscopy has been used to identify the actual product. For example, addition of HCl to 1-methyl cyclohexane can in principle yield either product 1 or 2. PMR spectrum of the product shows a singlet at about delta 1.5 for the methyl product protons. This confirms that the protons product formed in 1-chloro-1-methyl cyclohexane. Had the product been second, it would have exhibited a doublet for the 3-methyl protons at around delta 1.0. Distinction between geometrical isomers. PMR spectroscopy can be used to distinguish between cis and trans isomers. The distinction is based upon the magnitude of coupling constant trans protons and 6 to 14 Hz for cis protons. Distinction between inter and intramolecular hydrogen bonding. During H bonding, transfer of electrons occur from the hydrogen atom to the neighboring electronegative oxygen or nitrogen atom. As a result, hydrogen bonded hydrogen gets deshielded, the amount of deshielding being proportional to the strength of the H bond. The extent of hydrogen bonding depends upon the concentration, temperature, and the nature of the solvent. In concentrated solution, more molecules can come in contact with each other to form H bonds. As a result, in concentrated solution, hydroxyl protons absorbs around 4 to 5 delta, while in dilute solution, particularly no hydrogen bonding occurs, the absorption shifts to higher field around 0.5 to 1 delta. The extent of intramolecular H bonding, on the other hand, remains unchanged on dilution, and hence the chemical shift of the intramolecularly H bonding hydroxyl group remains unchanged. For example, salicylates and enol forms of beta diketones shows OH resonances at approximately the same delta values at all concentrations. Determination of relative amounts of tautomers. Beta diketones and beta ketomers exhibit ketoenol tautomerism. PMR spectroscopy can be used to determine the relative amounts of tautomers in a tautomeric mixture. Let us take the example of acetyl acetone, which consists as a mixture of keto and enol forms. Its PMR spectrum is shown in figure 2.20. Since the rate of interconversion of keto and enol forms is quite slow on the NMR time scale, therefore both keto and enol forms show signals independent of each other and are also well separated. The chemical shifts of various protons in the keto and enol form are shown below. By comparing the relative intensities of the CH2 and CH group signals possible to determine the relative amounts of keto and enol form from the spectrum. Total intensity of 6 methyl protons is 20 units. Intensity of 2 CH2 protons is 1.33 units. Intensity of 1 CH proton is 2.66 units. Percentage of keto form is 20. Percentage of enol form will be 80. And alternatively, 1 mole of keto form upon 4 mole of enol form. Basically, it comes out to be percentage of keto form 20% and percentage of enol form is 80%. Study of proton exchange process like conformational interconversion. Some chemical process occurred so fast that PMR spectrometer cannot observe them. For example, the rapid exchange of OH protons among the molecules of an alcohol and NH protons among the molecule of an amine. To illustrate the effect of such processes on a PMR spectra, let us discuss the PMR spectrum of a simple alcohol, ethanol. The PMR spectrum of ordinary alcohol shows a triplet due to the three equivalent methyl protons, a quartet at delta 3.62 due to two equivalent methylene protons, and a singlet due to hydroxyl proton at delta 5.37 as shown in figure 2.21. Thus, the spectrum of ordinary ethanol does not show spin-spin coupling between the hydroxyl proton and the methylene protons, even though they are present on the adjacent atoms. This is attributed to rapid exchange of hydroxyl protons between different ethanol molecules of the same sample. This exchange of proton is catalyzed by small amount of acetic acid and basic impurities present in the ordinary ethanol. Due to this rapid proton exchange, each hydroxyl proton behaves as if it is attached to a number of ethanol molecules. Consequently, the hydroxyl proton sees all the possible spin orientations of the hydrogens on the methylene group. Similarly, the methylene hydrogen see so many different protons on the hydroxyl oxygen. In other words, methylene protons see only one average spin orientation of hydroxyl protons, and hydroxyl proton sees only one average spin orientation of the methylene protons. As a result, neither the methylene proton split the single due to the hydroxyl proton, nor the hydroxyl proton splits the single due to methylene protons. Thus, rapid chemical exchange causes decoupling. However, if all the impurities present in ordinary ethanol are eliminated, the resultant ultra-pure ethanol shows the expected triplet for hydroxyl proton and a complex multiplet for methylene protons due to splitting by three equivalent methyl protons and one hydroxyl protons. This is due to the reason that complete removal of last traces of acidic or basic impurities either altogether stops or greatly slows down the proton exchange process, and hence coupling between hydroxyl